So it's great to have the opportunity to talk to you about the cardiac imaging part, MRI, that is being done. Some disclosures here, and so, oops, it was a bit too quick for you to see the cardiac images. So we have 20 minutes in that visit to image the heart in detail with MRI. And we can get a lot of information about the size of the heart chambers, the function of the heart chambers in very much detail. We can even get some information about the tissue in the heart muscle, and we can learn something about the flow across valves, the aortic valve, and about vascular stiffness. Now, unfortunately, unlike the brain imaging, cardiac imaging is quite difficult to analyze, and computers haven't really grasped how to do this properly. So we went to the British Heart Foundation and were very grateful that they gave us money to open 2 core labs for the image analysis of the first 5,000 participants that came for this MRI scan of the heart. And we've made great progress. So our teams were very tediously drawing around the edges of the heart to be able to measure what we are interested in is the volumes and the mass of the heart. And you can see there also drawn in the pre-chambers of the heart. And that gives us now opportunities. And I like to categorize that in 3 different types of opportunities. And I'll start with, on the left-hand side, the opportunities that are sort of the epidemiology type research that you've already heard about. And I'll give you a few examples where actually we can do research already on 5,000. There'll be more that we are interested to do in 100,000, but we can even start on 5,000 participants. So the first paper that we published fairly recently defines normal ranges of these measures in the heart that will be very useful for clinical practice, that we know, well, if, let's say, you fall for your ejection fraction, which is a measure of the pumping function of the heart, if you fall outside the normal range, you are in this red bar, then this is not normal and indicates maybe that you've got a heart problem. So this will be very, very useful for clinical practice. Also, my fellows have presented about last month at a European conference 2 abstracts that hit the headlines more than I actually expected. So one was about the impact of air pollution on the heart, and the other one of statin use on the heart. And I'll just show you a couple of slides on this. So given that we've got that information about air pollution, we can actually look at the impact on cardiac size and function. And what you can see here is that it appears to be that with air pollution, your hearts are larger than without air pollution. And that indicates sort of a negative effect on the heart. This study here, we looked at participants who took statins and participants who didn't take statins, and again looked at the heart size and function. And what we can see here, if you just look at the effect of statins on the heart without any other knowledge of that participant, you would think that the heart becomes thicker, which is usually a bad thing. But when you put all the information that you know about the participants in, what's their age, what's their weight, physical activity, all the things we know have an impact on cardiac structure and function, then you can actually see that statins protect you. The heart is not as thick and the heart is not as large. So other opportunities are related to also the challenge. So I know Americans always talk about opportunities when there's a real challenge. We have a real challenge in UK Biobank. We need to analyze 100,000, so we can't do this manually. So the BHF funded 2 people full-time for 3 years to analyze 5,000 of these images. And that would mean we need at least 40 people full-time for 3 years to analyze 100,000. And the other thing is that even if you train people up, they measure once and they measure again, and there's a slight variation. Now, we are quite good at this, but computers can be better. So clearly, because of the size, we actually need to find automated ways. And what UK Biobank actually allowed us to do is put a consortium together with an interest in this, including academics and industry, to tackle this. And we basically looked at the literature, what is actually available in terms of segmentation, these contours of the heart. And actually, researchers who request data now on the participants already get some automated volumes of the ventricle. And that is something that the scanner does itself with a tool called inline VFD13A. And we wanted to know how accurate is this. So as we were measuring these first 5,000 people, we looked at how often did this automated algorithm work. And it worked 91% of the time, but that also means that 9% of the time it didn't get it right and actually got it quite wrong. And so I think the message there for researchers that use this data, whilst it's very good, is probably you do need to do a visual check because there's sort of an almost 10% failure rate. However, Siemens are already working very closely and they have improved algorithms, so I'm very confident that in the near future that will be much, much better than as it currently is. So we are also working with other partners, and what we've done is those first 5,000 that we've analyzed, you can split them into 4,000 and 1,000 roughly, and you use the first 4,000 to train computers to analyze them, and then you have another data set that the computer doesn't know, and it basically tests how accurate it is compared to our manual contours. And this is with a company called Circle. They have basically, this is what a computer did in a few seconds compared to us drawing this for minutes. So this is very, very encouraging. And here, lots of numbers, but basically what this shows you is that there's very, very good agreement in these measurements that we have with very, very little difference. And this is even better than the ones that we already provide through the Siemens algorithm. And that is also the case for the right heart. So both for the left heart and the right heart, already we have made major progress. This is a group at Imperial College, Wenjia Bey and Daniel Rückert, who are doing similar work. We actually want people to compete to come up with better solutions. So this is an excellent solution, again, contouring automatically the left ventricle and the right ventricle, and also the atria. And this is pretty much as accurate as we can do it manually. And again, what they showed actually is very attractive. So if I'm measuring something twice, if I was perfectly in agreement with myself the second time, I would see a number of 1 here. So we are pretty good, 0.97 is very, very good. But actually a computer compared to a human is better than a human measuring it twice. So these numbers are larger than when humans measure twice, which is very, very encouraging. Just very briefly at the end, another opportunity that I see is there may be other things that we don't manually analyze that a computer again can look at that provide opportunity to get even more information about participants. And we haven't done this in UK Biobank, but I'm sure this will come very, very soon, is something that's called Cardiac Atlas. This is a statistical method to look at shape and function of the heart in different ways to what we do with our manual analysis. And this was a study not related to UK Biobank, where they looked at hearts in adults that were born preterm. And they could detect differences and sort of you can see how different they are from other people that weren't born preterm. And with that, I'd really like to thank you, all UK Biobank participants, the funders, the UK Biobank team, the UK Biobank Imaging Enhancement Group led by Paul Matthews, and the entire team behind our consortium of the image analysis. There's lots of people involved, but most importantly, thank you to all the participants.